Good afternoon, everybody. Welcome to this Energy Futures Lab lecture. My name's Tim Green. I'd like to welcome you on behalf of the Energy Futures Lab. I think many of you know us as an organization, but I'll say just a few words. Our role at Imperial is to draw people together from various strands of research and education in the broad topic of energy systems, and to help Imperial College be more than the sum of its parts. You know, for an organization that organizes, as universities do on discipline basis, it's a challenge for us to address the big questions and to draw together those discipline specialists to discuss the big interdisciplinary topics. And I think this evening's lecture is going to be a fine example of how that sort of thinking is important in tackling the big questions in energy. We organize ourselves across 5 themes, looking at sustainable power generation, cleaner fossil fuels, the use of sustainable transport, on innovation and policy, and on energy infrastructure. And this talk is going to fit into that 5th of the themes that I listed, a look at how energy infrastructure plays a role in optimizing energy systems as a whole. We have, over the years, organized many external speakers to talk on a wide variety of topics. You will see scrolling on the screen behind me some of the topics that we have upcoming shortly. Our next talk in this series is in a month's time. Jane Burston will be here to talk about commercializing energy technology. And it occurred to us a little while ago that we were putting a lot of effort into organizing high-quality external speakers and not perhaps making sufficient use of the expertise that's here on this campus. I've known Nilay for somewhat over 10 years, and I can't quite figure out quite how much over 10 years. I've had occasional opportunities to hear him talk, but I personally will greatly enjoy listening to one of my colleagues at Imperial discuss his personal area of research in some detail. So this is one of our early attempts to try to capitalize on the expertise there is across the campus, and I'm pleased to see so many of you here to hear this talk. We will be recording this talk. You can see the video cameras here, and we've got a YouTube channel with a growing catalogue of such lectures and events for you to look at should you ever not be able to attend one of them. So you just need to be aware of us filming and recording when it comes to the question and answer session at the end in particular. As I said a moment ago, I've known Nilay for something over 10 years, and we came together to discuss the need for Imperial to start capitalizing on the range of energy research that was on the campus. And those discussions led ultimately to a number of things, one of which was the formation of the Energy Futures Lab and of its education program in the MSc on Sustainable Energy Futures, but also in the launch with the generous funding of BP of an urban energy systems project. And Nilay was one of the leaders of that project, and I think he brings a very interesting perspective. His systems level approach to all sorts of engineering problems is particularly applicable in the energy sphere, and I greatly look forward to hearing his discussion of that this evening. So thank you very much, Nilay.
So thanks very much for that introduction, and yeah, it's quite an interesting experience for me as well, because normally I either teach undergraduates or master's students, or I'm presenting my work at conferences or to external people. So it's quite a pleasure, and I do like Tim's idea of having the opportunity to speak in front of you, and I hope we'll find some other people from around the college to do some similar things. So urban energy systems, it's, as Tim says, a piece of work which started around 10 years ago. I mean, it really got up to speed maybe about 8 years ago. And it was driven by a very simple hypothesis, which was around the question that we felt that cities were inefficient in their use of energy. And the simple question was, could you run a city on half the energy that it actually consumes and still do all the things you like to do in cities? So that was the question that we set ourselves. So why did we look at cities in the first place? Well, the interesting thing about cities is that if you look at how the world's population is growing, so this is the world's population, and then you look at the world's urban population, you can see they track each other. And essentially what's happened is, since around the year 2000, effectively every new person on Earth is an urban person. Okay, not the exact person, but on a net basis. Yeah. So around 2005, 2006, funny enough, when we launched the project, people estimated that the world was 50% urban and 50% rural, and that it's probably now about 52% urban. And what's happening is, you can see this is the world rural population. It's actually expected to peak and then decline while the world urban population grows. So the first big driver for this research is the fact that not only is the population growing and using more energy, but all those people are going to be living in some kind of city. The other thing was about cities themselves and how cities grow, decline, change, innovate, and so on. And I like this picture very much, even though it's tremendously confusing. And I showed it yesterday, actually, to some people from E.ON. And they said, oh, is that an underground map? And it does look a bit like that. And you'll have the slides, so you can study this at great length. But what this is actually showing is the so-called size rank. It's showing, by population, the rank of cities through time. And so if you look at Tokyo, which is this one here, it's been the world's biggest city since the 1960 and since 1955. This is New York, or the New York Greater Metropolitan Area, which for a long time was, the second biggest city, but it's been shrinking in its city rank. We've got these cities that are coming from nowhere to being the second biggest city. That's New Delhi there. Shanghai, in terms of rank, sort of going all over the place. So the interesting point is that cities are changing in terms of their sort of dominance of the global economic system. And in some ways, cities are competing as much as countries are competing. And that's a theme that you've probably heard a lot about. This is Chicago here, I think, which is sort of, was the third biggest city in 1950, and it's sort of disappeared off the list there. Now, immediately when people start to think about cities and research and energy and those sort of questions, one of the pictures that forms in your mind is the concept of a megacity. So something like New Delhi, or Tokyo, Mexico City. And, there are a lot of TV programs about how difficult it is to organize sustainable living in things like megacities. But the real challenge of energy systems, or sustainable resource systems, or sustainable development or economics in cities, it's about places like Leicester, Peterborough, Newcastle, and so on. Because most people don't live in megacities. So if this is the world population again, these are the rural dwellers, and these are the urban dwellers. So most people live in cities of up to 500,000 people, or 1 to 5 million people. So although we like to think about megacities and the problems of megacities, we won't solve the problems of urbanization by solving the problems of megacities. We'll do some really good work in solving the problems of megacities. But if you want sustainable cities, you need to think about these sorts of cities, because that's where most people live in the world, and that's where most people will continue to live in the world. Another interesting feature about cities is that most of that urbanization is happening in the developing world. And if we look at the Chinese average per capita energy consumption, or the Thailand per capita energy consumption, and compare it to the Beijing per capita energy consumption and the Bangkok, you can see that the urban dwellers in that part of the world use 3 times as much energy than the national average. And it's because of 2 main things. It's because they have a higher standard of living and more income. And second of all, they've got access to what people often call technical energy, things like electricity and refined fuels. So they've got access to energy, and they're able to pay for it. So we've got this trend of more people moving to cities, and when moving to cities, they're actually using more energy. There's another pattern, which I'm not showing there, which is when you consume energy in a city, it's much more time fluctuating than the national average consumption of energy, especially electricity, because cities don't tend to have the big industrial processes that consume electricity, but heat as well, in a much flatter way through the day. So you're not only using more energy, you're using it in a more peaky way. So the ratio of the peak consumption to the base is also changing. So cities, of course, from an architectural perspective and a form perspective, are all quite different, and they all have their unique features and their landmarks. But if you think about it from an engineering perspective, then you wouldn't really be able to say which is which anymore. So from an engineering perspective, which is, of course, the perspective that I'm qualified to talk about primarily, they're much the same, and the problems are much the same. And one of the problems is energy efficiency. And, of course, there are multiple ways of looking at energy efficiency. This is a very classical view, a Sankey diagram, which I think many of you will be familiar with, which shows primary energy in different forms. These are units. I can't remember what, but it doesn't actually matter. And it's just showing it in terms of energy into the system and energy actually at the end use of consumption. So if you look at Toronto, people using energy in three main forms: electricity for appliances and various other use of electricity, heat for buildings, maybe to some extent for process heat, but primarily heat for buildings, and of course transport. And this is the wasted energy. So accounting for what's come in, about half is wasted. So we might say that Toronto's 50% energy efficient. 50% of the energy put in at the top ends up being used what it's meant to be used for. So that's the basis which uses the so-called first law of thermodynamics. The energy is conserved, it just changes its nature. So 50% is used and 50% is wasted. If we consider the second law of thermodynamics and something called exergy, which measures not only the quantity of energy, but also has a quality feature to it. And here we look at analysis for Vienna, which looks at how much exergy goes into the system, 171 terajoules per year. So exergy that goes in at the top in this form is what's called very high quality energy. It has an exergy quality of 1 or close to 1. In other words, it's a very high value energy flow. And we look at how that is used. So low temperature heat, which is a big amount, process heat, a small amount, and light and motion, which are work in thermodynamics. The actual useful exergy delivered to the end user is 31 terajoules per year. And this energy efficiency is now 18%. And our own analysis of London comes up with a figure like 20%. So why is this the case? Primarily it's the case because we can take something like natural gas. If we burn natural gas, the flame temperature will be more than 1,000 degrees. And we use that to keep a room at 25 degrees. And what exergy tells you, it tells you that if you have heat available at 25 degrees, there's hardly anything you can do with it. But heat available at 1,000 degrees, you can do lots of things with it. You can drive chemical reactions. You can drive steam turbines to make electricity. You can drive heat pumps and so on. So cities are not only wasteful in terms of the volume of heat, but they destroy the quality of the energy. So in principle, this high-level analysis says, yes, you probably ought to be able to run cities on half the energy that they consume, but it's probably a lot more difficult than that. So cities not only are inefficient, but they are big polluters. So these are the greenhouse gas footprints of different cities in the US, and you can see, some of these cities are pretty big polluters. They also create other kinds of pollution. So, a lot of the focus on emissions is in terms of greenhouse gas emissions, but actually the emphasis on air quality seems to be coming back, and you can see these areas which are pink or brown or orange are areas where there are breaches of World Health Organization guidelines on particulate matter emissions. And so you can see those breaches are very much associated with big urban populations. Cities also, so those are the direct emissions of cities. Cities also are centers of consumption. So they're very dense in terms of people living close to each other. And so not only do they consume energy, essentially, so this is energy consumption of the city in blue, which is being consumed in an inefficient way. That's the energy that goes through the city walls, if you like, in some form, 50% of which I told you is wasted, or perhaps 80% of which is wasted. They also consume a lot of energy indirectly by the goods and services, so the food, the manufactured products, the construction materials and so on that come into the cities. So the embodied energy that comes into cities is also quite large. You can see that's particularly the case for Tokyo, which is a service-oriented city, so it doesn't do any of its own manufacturing. The Chinese cities less so, because they will do some of their manufacturing within the city, and so those emissions or energy consumption are counted in the city. So that's the bad news. There is some good news, but it's also bad news, I suppose, which is to do with how densely cities can produce or consume energy. So it's a bit of a confusing picture, but if I spend a minute or two, I think you'll understand it. So these are different potential ways of getting energy that could be used in cities. So we could use biomass through photosynthesis. Now, the energy density of photosynthesis is of the order of a watt per square meter, roughly speaking, maybe a bit higher than that. And so photosynthesis, to produce energy, requires a large footprint. And the problem is a city consumes energy at a much higher density. So it's of the order of 10 watts per square meter. Okay? So city is quite an energy-dense thing. So if we said, could we use the green space in the city to grow biomass to fuel the city? The answer is no, because the amount of land you'd need would be much bigger than the city itself. Could we use PV? What if we covered all the roofs with PV? Well, if you covered the whole city with PV, so you didn't actually have space for anything else, you could just about make it work, because you can see the energy density of PV is more or less the same as the energy density of a city. So you could theoretically. But realistically, how have cities come about as they are today? They came about because they're fed by these much more energy-dense things that sit up here. So the only reason we've managed to sustain the cities that we have today is that we've had things like oil fields, coal fields, power generation, which all have this very high energy density, and therefore in the hinterland they can feed the cities. So it's interesting to see Paul Rutter in the audience, who has a lecture on the history of urban energy systems, and he explains that London became very constrained in its growth and development because of the wood fuel supply chain. It was basically deforesting the whole Thames Valley, and then along came coal and the Industrial Revolution, and that gave London a bit of a kickstart again, for better or for worse. So this energy density is very interesting because it provides big opportunities, because we're using different forms of energy and converting it close by. The big opportunity is to take some of that wasted energy and somehow reuse it, because a lot of that wasted energy is in the form of heat, and if only we could capture that heat and use it for something, we would avoid generating heat somewhere else. So, in a sense, the biggest leverage is from systems integration. It's from integrating systems that generate waste heat and systems that use waste heat would be the quickest way to get rid of a lot of those inefficiencies. However, that means possibly engaging hundreds of thousands or maybe even millions of people to change something in the system. Not only that, but the policy is very fragmented. So if you look at energy policy in countries, they're mainly supply-side policies rather than things to do with the detail of how cities operate. And the reason for that is you can get 5 or 6 chief executives of big utilities in a room, thrash out a deal with them of some kind, whether it's about renewables or decarbonizing or affordability or whatever the challenges are. And after a few hours, maybe you can make progress. This kind of thing is not something you can resolve in a few hours. Nevertheless, of course, we don't need to be too defeatist about that. We say, well, that's a very interesting scientific and engineering challenge. What can we actually do about it in a practical sense? And my own background is very much in modeling different kinds of systems. So one of the things I was thinking about a long time ago was about refineries and petrochemical complexes, which are, to some extent, like small cities, but they're different as well. But certainly, what was interesting about them is if you compare a typical complex from the 1970s to one today, then the one today will use less than half the energy and less than half the water for the same amount of output because of going through a series of these systems integration processes. So what I was thinking was, they look and feel a bit like cities. Why can't cities go through that same transition? And of course, one of the big differences is that in a refinery or petrochemical complex, there's one person there that's responsible for the water bill and one person that's responsible for the electricity bill and one person for the gas bill. And if they can be persuaded that these methods are going to save them 50% of the bill, they're up for it. And so they'll go through that process. Of course, in cities, millions of people are involved in millions of activities that result in the consumption of different kinds of energy. And so we thought, well, let's not worry about that. Let's try to grapple with that complexity and start to think about how can we start to model cities. So we started to think about how we modeled these complexes. And of course, when you come to trying to model cities, you have to think about things quite differently. So it took us quite a long time to come up with something, but we eventually came up with this framework, which has these 4 levels in a hierarchy. So the first thing about a city is to understand how is it organized. What's the spatial plan of the city? What sort of things like economic activities take place? Where do people live? What kind of buildings do they live in? What are the climate features, the geographical features? How do people actually interact with this 3D space? What do they actually do? And how do those behaviors result in energy consumption? How can we change the way resources are used, flow, and converted in a city? And then how can we take all of that and layer onto it a very smart infrastructure? So a lot of people talk about smart cities. And one of the things that slightly annoys me about the offerings that people have in smart cities, or the things they talk about in smart cities, is they jump straight to this. So they talk about, we can put in a lot of ICT infrastructure, we can put in sensors, maybe we can put in some kind of actuators, and we can make various changes in the way systems work. And that is, of course, one dimension of smart. But actually, a really smart city has to think about all of these dimensions. And then it's a, in my mind, a truly smart city. So we're looking at these sort of questions. Oh dear. Yes, I'll remember to silence that next time. 2 big questions. One, how do these things give rise to demand for resources? Because, of course, we don't use energy as an end in its own right. It's a means to some kind of end. And then, can it be reduced? And, of course, then we get an irreducible amount of different kinds of energy that are needed to drive these systems. How do we supply that in an efficient way, which might be lower carbon or more cost-effective or whatever is your criteria? So these are the things, as I say, that we try to model in a city. And we've developed a framework and a software tool called Urban, which is trying to capture these different kinds of models. A layout model around which is about the space, an active agent model, which is about people and behavior, a resource technology network model, which is around conversion and flow of resources, and finally a service network model, which is about the actual engineered networks that will deliver these other things. And I'll talk you through some of these and give some example. So the first thing is you need a good and appropriate representation of some temporal effects, because, as I say, the consumption of energy in a city will vary by time of day, by season of year, and you need to capture the spatial effects, that different things are going on and there are different needs in different bits of the city. You need to be able to capture the energy chains and how energy is converted. So the fact that you might be trying to deliver heat and electricity, and there might be different ways of actually supplying those in what we call a superstructure. So this is showing different ways of potentially providing heat through a gas boiler, a wood chip CHP or a biomass boiler, and different ways of producing electricity. So we need to be able to have a generic way of building up these energy chains. And then, of course, we need to zoom in on the spatial things. So I'll talk a bit about the land use and the built environment. So here we've looking at it in 2 ways. In one way, how do we represent what's already there? So that's already a well-defined science of geographical information systems, and there are a variety of different city modeling frameworks which tell us what is in a city. But what we also looked at, because a lot of people were interested in, was how would you design or redesign a city? How would you reallocate land use, or how would you design a city from scratch? So there we developed what's called a layout model, which essentially places things in space. So residential buildings, commercial buildings, institutional buildings, and so on. and also accounts for the fact that people need to circulate around. So we need a transport infrastructure based on where we think people would be likely to move. And we solve this as an optimization model. It has a lot of features which are similar to chip design. Because when you think about how you design chips, you like the components that need to communicate frequently with each other to be close together. And that's actually very much a feature of a well-designed cities. It's got this well-connectedness that people have access to the services that they need. So we worked with the developer to apply this method. So this is an eco-town which is to be planned, was scheduled to be built about 40 miles north of London. It never went ahead because of the financial crash. That's another story. So the developer came up with a good low-energy configuration, much less than half the average energy consumption of London, and this was through their design. These numbers are representing the density of development in terms of dwellings per hectare, and these are various types of land use. And they said to us, so how well can your model do? And we said, oh, well, let's put it through. And we put it through the system, and it came up with this 3-village design, quite high density. And we said, oh, we'll consume 11.4 gigajoules per capita per annum. So very low energy configuration. They said, oh, it's very nice, but completely unlivable. So no one will actually want to live there. So they gave us some livability criteria. How far can you be from a primary school? 800 meters. What's the maximum density of development? How much mixed-use development you can have, and so on. And so we ran that back through the system and came up with a design like this. It's like a two-village configuration with some green space in between. And they really like this one. It's not too different from their original plan, but it's somewhat lower energy consumption. So we found that to be a very interesting exercise, and it gave us one of our first tools. And in doing that, we had a look at some other work that was going on. And this is some research that was looking at not so much greenfield, but smart growth. And I'll zoom in on these two places because they're both quite interesting. So Portland and San Antonio are quite fast-growing cities in the US. In fact, for some time, I can't remember the time period, but it's only in the recent past, last few years, San Antonio is the fastest-growing city in the Western world. So its population is growing very fast. But the policies are very different. So Portland, you may know it as being a beacon kind of green city. It has very strict planning guidelines. And so its population has grown a lot. And this is the population density, these different colors. Blue is high. So its population has grown a lot. But actually, its carbon footprint has gone down from 6.5 to 5.5. That's the transport carbon footprint. And then this is the total carbon footprint. San Antonio, you can see it's grown outwards in a very different kind of way, non-smart growth, and you can see its carbon footprint is quite a lot higher, at least the transport footprint. And you can see this with Toronto. This is the energy consumption. You can see that in the more sprawling part, you can see that much higher energy consumption. The same specifically for transport energy, you can see that the cities that are sprawling cities which have co-evolved with the car are high energy. This is energy consumption for transport on this axis, and this is city density. So you can see it's a very strong correlation. You can see European cities being here and some Asian cities sort of being over here. So the first message about cities is get the land use plan right. And whether that's a new city, an existing city, or a growing city, see what you can do with the land use plan. Within that land use plan, what can you do? You can do quite a lot with the built environment. So this is showing what can you do in terms of reducing carbon emissions from the built environment. So within the land use plan, you can then go and say, well, I can still make my buildings in that plan much more efficient. So this is just showing improving the built environment even further, and using low embodied energy materials. So this is the embodied energy, and this is the carbon emissions from heating in particular. So two big things you can do with a housing stock is reduce the emissions from heat by making them thermally much better performing, and secondly, very much for new builds, using lower embodied energy materials. So you remember I showed you that picture of the indirect energy consumption of cities. If you have on-site generation, of course, you can offset some carbon emissions as well. Does it work? So this is an actual real study in Frankfurt where they retrofitted this street of 1950s type buildings. So they look like this now. And using thermal imaging and then also just looking at the energy consumption, Bill, you can see the thermal imaging shows much less heat loss and 87% reduction in heat consumption. Now, this is not easy to do, and the reason is that it's a craft industry today. So one of the big challenges, which is not a technical challenge, it's more of a business model challenge, is how can we transition this thing from being a craft industry to being a lean manufacturing industry? So if you think of the fact that in Western Europe, a lot of people in the 18 to 25 age demographic are looking for jobs, you could see that this could be a very good thing for them to be doing. Next level, so we've spoken about land use. What about people? So modeling people is not easy. There are many frameworks for modeling people, and there's a lot of computational social science that looks into that. And one of the popular frameworks is agent-based modeling. So one of the things we've built is an agent-based modeling framework which looks at how do people use this 2D or 3D space? What are they doing at any given time of day, and how does that give rise to resource consumption? And I'll just show you an interesting study. This is London, and it's looking at commuting patterns. And I don't know how many of you can see the scale, but anyway, this is the traffic density in London at different times of day. There's a morning peak, a bit of a lunchtime peak, and then a kind of smeared evening peak. So you can see that congestion will arise when you have these high peaks. So we asked the question, what if workplaces staggered their start times a bit? What would happen? So which is sort of what happens in Germany, for example. They're much more staggered start times. Reran the model. It brings down this morning peak a bit, and it spreads the evening peak a bit better. But we were asking the wrong question. The question we should have said was, what if schools staggered their start times? Because actually, what's driving a lot of this peak is the school run. So anybody who's driven in London in and outside term time will notice the enormous difference. Now, you know, we haven't run that case because that's one of the interesting things about modeling. Sometimes you end up asking the wrong questions. But that's the kind of thing you can do with these models, is start to predict different kinds of behaviors. Next level, which is resource flow and conversion optimization. So let's say we've modeled what people are doing. So we know when they're at home, when they're at work. So when they're at home, they may need some appliances to run. They may need the house to be warm. When they get to work, they'll switch on the lights, switch on machines, and so on. So we can start to predict by space and time, where are we going to need energy services? Where are we going to need cooling, heating, transport energy, and so on, electricity. And we can start to think about how do we supply that in a better integrated way. And we built this model called Resource Technology Network Model. What does it do? It takes these demands. It takes the so-called available energy resources. So these are things that we can bring into the cities. We can bring electricity into the city. We can bring coal, gas, biomass. We also have some resources within the city. We might have water bodies that can be used for heat exchange or heat pumping. We may have ground source. We may be able to have sunlight. And then the key point is to have a catalogue of conversion technologies, which are things like converting gas to heat, gas to power, gas to heat to power, things like fuel cells perhaps, heat pumps. So whatever are our energy services, chillers, absorption chillers, electric chillers, whatever our energy demands and whatever our resources available, we need these conversion technologies. So what we do is create a superstructure of these conversion technologies. And then what the model does is it tells us what conversion technologies we should buy, where we should put them in the city, and then how resources should flow in and flow out. So for example, you might have electricity and water flowing into some kind of chiller, heat exchanger system, and very cold water flowing out and going somewhere. And this will be a bit clearer when I give you an example. So this is a new city development that we worked on with some collaborators in China. It's near Shanghai, and it's an interesting city because it was designated a demonstration city, low carbon, no coal city. So no coal was allowed to come into the city, and no electricity which was generated from coal was supposed to be used in this city. So it's got four zones. And what's interesting is it's cold in winter and hot in summer. So when we ran it through the model, and the model had all these catalogue of technologies, it shows two technologies in particular. One was a large-scale, district-level, gas engine, ground source, heat pump, reversible. What does that mean? It's a gas engine which in the summer abstracts heat from the built environment and dumps it underground, and in the winter essentially abstracts that heat and puts it back into the buildings using a network. But also a similar smaller scale technology, which is a building level for large institutional buildings, gas engine CHP system, which can run with a heat pump in both modes, heating and cooling modes. And this is showing just how those run in summer and winter with big GHG reductions. And if you remember those 4 zones, they're now connected up by a network, which is a district heating and cooling network. Now, these networks are very easy to build when you're doing greenfield developments. They're somewhat harder to build when you're doing retrofits. But that allows us to supply heating in winter and cooling in summer using the same networks. We've got 2 different pipes running through this network. And you've got some robustness in the sense that if any of these subsystems might fail, there's still a way of distributing heat or cool throughout the system. What does it mean in practice? We've shown that when you look at the simple systems that we have today, and we use a normalized energy consumption, that different interventions like improving the land use, using distributed generation, improving the building efficiency, optimizing the resource flow, can easily get you from 100 to below 50. So coming back to our original hypothesis, yes, with a variety of what I would call smart interventions, you can run cities on half the energy. It does mean that you switch a little bit from operating cost, which is this dark color, to capital cost. So you can see that these kinds of solutions here require you to spend money in the city. And that's one of the issues which means there is a logjam, because why would we run a city on twice the energy that it needs? It doesn't make sense. But to get the change does require people to give it a lot of their attention, first of all, and second of all, to spend money. And at the moment, we haven't really got the systems in place to help us spend that money. This is a study we did for Haringey. So Haringey has some quite poor wards in it. This is one of the quite poor wards in there where a lot of people live in energy poverty. And this is showing the energy consumption. And we showed how different interventions in the system would eventually get them to a system where people would need much less energy to do the things they need to do. And again, the question was not a technical one. It was, how is Haringey going to finance that process? That's what they're working on at the moment. And a similar study for Newcastle, looking at how to reduce heat demand in Newcastle. Again, lots of interesting solutions there. Some of these solutions, interestingly enough, when we look at them on a whole life costing basis, don't actually cost any more. So we have to spend some capital, but it pays back. So I don't know how many of you are familiar with the concept of marginal abatement curves for carbon, but it's a way of saying if we want to reduce the carbon emissions from a system, how much do we have to spend per ton of CO2 abated? So if we look at a city district in this case, and this is our baseline, if we consider the baseline being what we call a 2020 baseline, a city that is using a 2020 assumed energy system, and we're trying to decarbonize it, one of the questions we're looking at is how much decarbonizing should a city do itself, and how much should it ask the national system to do for it? Because that's one of the other interesting questions. So a city can run at half the energy that it needs. And one of our other questions was, do you decarbonize the city by doing stuff in the city, or do you just decarbonize the national energy system somehow? For example, you just have hydrogen for transport and heat, maybe biofuels also for transport and heat, and zero carbon electricity. So you do everything at the national level and just let the city take those low carbon energy vectors. But what we found was actually up to 50% of carbon you can get rid of without there being any cost over the whole life cycle. In other words, there's a negative abatement cost. So this correlates quite well with work done by Siemens and McKinsey that show that a lot of energy efficiency and cogeneration and small-scale renewables and so on, which are things which tend to be used in, or would be used in cities, are the things that are in the left-hand side of their so-called abatement curve, the negative abatement cost opportunities. So these tell us that against this 2020 baseline, we can decarbonize quite efficiently in cities. And this shows how technologies for heat might change. So we might initially start with some small-scale combined heat and power, some domestic air source heat pumps, and some boilers. And eventually, as we try to decarbonize, we see these district-scale gas engine heat pumps, again, similar to the thing that we were looking at in China. And then once we get to 50%, it's showing we need to rely on low-carbon electricity, which is coming from outside the city. We can't do much more in the city. And against a 2030 baseline, where we're assuming things have changed and it's already quite a low-carbon city, this is all relative, then it says, yes, you know, everything starts to cost money. But that's against a very good baseline. I think this is the curve to focus on. And so that allows us to start to look at some of these questions around not only what does it cost, but how can you get there? And I think what was really interesting for me was the fact that by bringing together a group of really talented people from different disciplines, so we had civil engineers, transport engineers, electrical engineers, process engineers, business school, and social science, we were able to put together a team that could take that very complex question that we originally asked ourselves and come up with some really quite clear answers in the end, which gave us a lot of encouragement to go further. And so now we have a lot of other projects that have spawned off from this original project, all of which are looking at some kind of aspect of improving the performance of cities. And so one of the things that is going to be set up soon at Imperial, I don't exactly know when, maybe Tim knows, is a Urban Systems Institute, isn't it? It's in the offing, so some of this thinking will be feeding into that. So, summarize, cities are really interesting because that's where I think the big battle against climate change is going to have to take place. And of course, cities are also one of the most vulnerable things to climate change. Not only because they are the place where a lot of energy is consumed and where a lot of people are going to live, but also two other things. First of all, a lot of innovation is going to take place in cities because that's where there's money, that's where there's people with skills, but also sometimes the nation-state decision-making is lagging the city-level decision-making. So cities are often more aspirational than the nation-state. The mayors are high profile. They want to get things done. So, you know, London is actually a good example of that, but, you know, there are many other cities that we've been talking to that have that same profile that sort of tell us that for some of this energy systems work, the natural governance size might well be the city. And finally, our little contribution here, which is that tools that can help us make better decisions are becoming available. And since we started the project, we've seen there's this big explosion of research in lots and lots of places around the world on cities and energy systems. So this is our book that James and I edited, and some of you are quite familiar with. This is another book edited by Arnold Gruvler and David Fisk, also from Imperial, called Energizing Sustainable Cities. And you'll see that there are increasingly more and more books and publications coming out. So thanks very much for your attention. I'm happy to answer questions.
Indeed, we've got time for some questions, so who would like to set the ball rolling? Oh, can you, I should say, can you just wait for the microphone to reach you, and could you please introduce yourself briefly before your question?
Hello, I'm Olivia. I'm currently just living temporarily in London, and I'm writing my master thesis on light-duty fleet electrification. And I'd like to know, in these tools you have been using, these optimizing tools, to what extent does the electrification, not only for the vehicles, but for the whole energy system, to what extent does this contribute to a greater energy efficiency? I mean, since you can concentrate everything in one single place, and also from the point of view of climate change, assuming that one day we'll be able to do carbon capture and storage. So that's basically what I wanted to know.
So good question. So we've looked a lot at electrification of heat and transport. So once you have a modeling tool like this, you can look at some interesting questions. So we looked at, for example, the concept of an all-electric city, because we can say, what resources can we bring into the city? So we say, what if we only bring electricity in? The big challenge there is to do not so much with the average energy consumption through the year, but it's to do with the temporal variation of energy consumption. Because you need to deliver heat and you need to charge vehicles sort of at the time of demand, and because that tends to, the thing about cities is they have these organizational structures that mean that people tend to do the same thing at the same time, like the people driving in the morning. The big challenge becomes the ratio of the peak demand to the base demand grows enormously, and if you do that in a simplistic way, you would actually need to double, if we take the UK as a case study, you would need to double or treble the number of power stations we have in the UK. If you added carbon capture, you would have to add yet another fleet. So you might need 4 times the number of power stations. So that says you need a much more sophisticated system than, if you think back 10 years, people were saying, well, one simple way to decarbonize heat, everybody would scrap their gas boiler and they would have an air source, or maybe ground source, but mainly air source heat pump. So if you did that, you would end up with this huge fleet of power stations, which only run probably 20% of the time. So you start to need to get into some more detailed temporal modeling, like understanding how can you store heat, how can you store electrical energy, probably, how can you change the way people behave so that they don't just want to do things on demand, things that are discretionary, like doing your washing, charging your vehicle, or any other things. Can you use new technologies like phase change materials to give you a lot more thermal inertia? So, for example, you can keep buildings warm at a lower level than, if you come in and you have a gas boiler, that can kick out maybe 30 kilowatts. So you don't need to do very careful planning, just come home and switch on the boiler. You can't really do that with a heat pump. So you start to get into, thinking into sophisticated management of the system becomes the real challenge with the electrification. But yes, you can get rid of point source carbon. I think in practice, a heterogeneous system is going to be more efficient, one that can use combined heat and power, one that can use biofuels, one that can use hydrogen, is much more likely than the concept of the all-electric city. But there's no question that increased electrification will be one of the outcomes of a strong climate mitigation strategy, but it won't be 100%.
We'll go here.
Hi Nilay, Mark Workman from the Energy Research Partnership. You've been doing a lot of your modelling about optimising energy consumption, bearing in mind that we're locked into a certain amount of climate change as it is, and most cities are very close to the coast. Have you actually started integrating resilience and adaptation measures within your energy systems modelling? I mean, for example, Sandy taking out Lower Manhattan and all the banking district down there and stuff like that. Has that sort of been built
just
in?
Beginning.
And does that impact on your optimization that you find?
Yeah. So it's just beginning to. So one of the interesting things there is this issue of how much redundancy you need to build into the system. For example, I showed you the spatial map. So one of the things we started to realize is actually the terrain and the altitude of different installations. Do you want to put things on higher ground? And those kind of questions start to become important, which we hadn't originally thought about. So yeah, it's a good point. And how near the shore do you want to put installations? These kind of questions start to become quite important. We are, because the problem with that again is it goes back to the same sort of issue. It's not about average data. It's not about average weather conditions. You actually need to somehow include in your scenarios extreme weather conditions to see to what extent. So you start to get into hydrology and things that we haven't done so much work on.
Okay, question at the front first.
Hi, Professor. I'm a PhD student from civil and environmental engineering. I'm quite interested in the agent-based model you mentioned in the presentation. So I want to ask, what kind of rules you used in the model? That's first question. And the second question is, as you mentioned, the people's behavior is quite it's difficult to model. So how can you handle this complexity? In other words, how can you handle the uncertainty of the model? Okay, thank you.
Yeah, good question. Take half an hour to answer it properly. So the big challenge in modeling always is to find the trade-off between representing your system accurately enough and yet not overwhelming it with complexity. So you have to always think about, what question am I trying to answer? So the questions that we were really interested in was, roughly, what are people doing in a spatially and temporally resolved way? And the what are they doing, we're only interested in the things that they're doing which have some energy implication. So if they're moving from A to B, where is A and where is B? And what mode of transport might they be using? So that gives you some interesting questions that you want to look at, which fortunately in the transport literature they've done a look at, which is called, activity choice and activity location and mode choice selection. And so there's the whole literature on discrete choice. What am I likely to be doing as my next activity, and where am I likely to do it? There's a variety of models to predict that based on some characteristics of the agents. So then that tells us, what characteristics of the agents do we need? Well, we need good enough characteristics to parameterize those models. So that allows us to create what we call a synthetic population. It's a population of people that are not all the same. They have different characteristics, socio-demographics and so on. And then we want to know a little bit about the places that they go to. So what kind of houses do we have? So that's somewhere between the built environment and the choice. And then the places they go to, again, what kind of places are those? So that when they're there, we can get an idea of the energy implications. So fortunately, the literature that's very helpful in this field is very much in the transport choice model literature, which looks at things like, what are people likely to do, where are they likely to do it, and how are they likely to get there? So that's the kind of model that we use. They aren't. They're typically what are called 4-step models. But what you can do is you can take the logic from those models and essentially embed that logic into agents. Because those models are just saying, probabilistically, what are people likely to do? And you can take that same probabilistic choice and embed that in the agent behavior.
Lady in the middle there. Can you just wait for the microphone, please? Thank you.
It's a very quick one with
Good.
a 1-minute answer.
Good.
You showed the cost of reducing by about 50% the energy consumption, and there is a cost at the red band. Is that capital cost or operation
Yeah, that's a good point.
Cost?
I've got a graph which shows that. So what's interesting, this is the actual, so this is the energy consumption, and this is the annualized cost of capital and operating. So operating is the dark, and capital is the light. And the problem is, particularly, if we look at this optimized, which is really want to look at, the problem is you need to spend quite a lot of money, and then you'll save money. And that's why all of us live in houses that are less efficient than they really should be. Okay, we haven't got round to improving them, but somehow we're not good at whole life costing as individuals, and actually as organizations and institutions. So we won't necessarily buy the most efficient X, Y, or Z, even though over the whole life it's going to be more efficient. So one of the questions, which I know people are looking at, is what kind of business models and funding streams can unlock this kind of funding so we can invest this money and then reap the benefits.
Yeah, just part B. It's when you do all this simulation, which kind of alternative forms of energy you are considering?
Essentially, it's everything. So every single case study that we look at, the modeling framework that we developed is a generic one. So we have the concept of a technology, and all that the technology does is it has a set of sizes, a set of capital costs, a set of resources that go in, and a set of resources that go out. And for each of the resources that go in and go out, there's some coefficients like how much goes in and out. And essentially, you can connect these up into a very complex network. And then what the system does is the model chooses which of these technologies I'm going to bring into the city, how big they're going to be, where I'm going to put them, and then what resources flow through them. So in terms of choosing which, let's say, primary energy sources we would want to include, that's up to the user of the tool. They can choose any number: wind, wave, biomass, solar, gas, coal, nuclear electricity. And one of the interesting things is to try different things, essentially.
Okay. This half of the room is doing terrifically well on questions. This half of the room, please. The question just here.
Hello, my name's Bora. I'm a PhD student here at the Center for Environmental Policy at Imperial. Sort of following on from the question here, like what you're saying in this graph, it seems that what's required is a higher upfront capital cost. And so my question was, other than looking at the business models, do you also consider the sort of legal and policy implications for how do you get that capital to be invested? Because in somewhere like the city you were talking about in China, the government has a lot of capital they can spend and a lot of legal authority to do that sort of development. But maybe in somewhere like London, you have a lot of individual property rights which would conflict with these sort of large-scale infrastructure developments.
Yeah, very good question, and it absolutely comes down to the governance structure in the city. So Peter and I, we were recently at a workshop where we were comparing different cities. So it was Gothenburg, London, Cologne, and Rotterdam. And what was amazing was just the systems that they have in place for getting things done, for funding, for authorizing, are so different that you can do completely different things. So Gothenburg, as a city, operates almost as a country. It has a treasury, it issues bonds, which are its own municipal bonds and green bonds. It owns more than 50% of the real estate, so it can essentially issue a green bond. And when it did that, they sold out in half an hour because they're in Swedish crowns and they're backed by the treasury. It can then use that bond to set up a company that refurbishes its own building stock, and it will, of course, reap the benefits over time, and it will easily be able to pay back the interest rate and the capital on the bond. So that kind of model works really well in a place like Sweden, which has that kind of organizational structure. Come to London, and it's about how can we get an environment which could unlock, that kind of investment. Are there some big sovereign funds, pension funds, those sort of things that could somehow set up a business to do this? Much more complicated. So Imperial College obviously is not the place which necessarily has so much of that expertise, although I can see Richard in the audience who can probably say a lot more about that. So in that specific project where we had that workshop, which is part of a European Union project, we're working with the LSE who are looking at those kind of questions. So we're looking more at these are the kinds of systems that you could bring into the city. This is what they'll cost, this is what the benefit would be, but how you would do it, certainly in our group we're not doing quite so much of that work, although it's extremely interesting work.
A question over this side now.
Fred Stewart from the Policy Studies Institute. You're presenting a very compelling case for what I would call a radical efficiency strategy for addressing ambitious mitigation targets within the next decade or 2 decades. And the question is why this very persuasive approach doesn't have the same resonance within the policy world that it ought to. And now, you offered one explanation that it's easy to focus on the supply side because you can pull in a few CEOs. But, I mean, the fact is cities, it's not like you're dealing with consumers. I mean, you're dealing with also a manageable number of organizational entities. So in that sense, it should be tractable as far as the policy system is concerned. And so it's your reflections on this slowness in engaging with this that I'm interested in.
So I think the problem is that if I reflect on that, then I've spoken about the city as a homogeneous thing. Actually, if we think about it as a distribution of entities that consume energy, then we've got a distribution with a very, very long tail. So if we think about the front end of this distribution, I'll talk about one company we work with, Sainsbury's. So Sainsbury's, we're working with them on this. They're up for it, they're spending money, and they're doing it, and they're bringing down their energy consumption and carbon footprint, because of course they pay the bill. But the big part of the tail, eventually, it actually has to touch the householders, because someone's got to come in and do some building retrofit, take out a boiler and put something else in, a fuel cell or a heat pump, or connect you to a district heating scheme. So I think the problem with the cities is that there will come a point where you can't get away from that long tail, and that means interacting with each one of us in this room and the other 8 million odd people, or 3 million odd households in London. So yes, on the left-hand side, absolutely right. Every hospital, every school, university, big commercial, you know, they should really be doing it and doing it quickly. Some are, some aren't. One of the big beefs I have, and you know, is actually the government's own estate, which, you know, when you add it all up, it's a huge thing. You know, that should be where we should maybe be starting to demonstrate and to build up the whole supply chain of how you do this. So I think that side you can deal with, and things are happening, but the long tail, I think that's the very complex and messy bit. So it's very stratified, and probably you need different approaches for those different bits.
Going to go to the back for a question now.
Andy Boston from Energy Research Partnership. I'm interested to hear what you've got to say about carbon lock-in and whether some of the technologies that look good early on, for instance, you mentioned gas CHP, then could become a problem as you decarbonise the grid, and therefore you're changing them again, and how you sort of manage that long-term versus the short-term tension.
It's a very good question. So there are certain technologies which you might be able to get their technical life out of them before you need to replace them because of a carbon constraint. And there are other technologies that may well cause a big problem. And actually, you know, the obvious one is what would we do with gas boilers? So let's put gas boilers to one side. You saw this transition. Whoops. So this orange space is saying if we want to get serious about decarbonizing, we need to go to district level, large-scale gas engine heat pumps. Now, the good thing about those is that whether they're in CHP mode or in heat-only mode, they're quite replaceable by some lower carbon drivers. So it could be an electrical heat pump, or it could be, you know, driven by hydrogen, but you're bringing that gas and combusting it at one point, and then you're serving a community with heat and power. So you could eventually even completely decommission that thing, and you've still got, for example, a heat network which you could connect up with some other heat network, and then that could be connected up to a much more remote, let's say, CCS power plant or nuclear power plant, which has got the waste heat. So the way you can model these things is if you have a pathway model, which not only looks at the near and the mid-term, but the long-term, you can make sure that your near and your mid-term investments are not necessarily going to cause you a lot of problems for the long term, but actually will help build the infrastructure that can get you on that way. So it's very dangerous to build models that look out to 2030 and say, how can we get rid of 30% of carbon, let's say, without thinking about how compatible that is that also with getting rid of another 50% of the carbon after 2030 or wherever that is. So the key message there is if you're building models of energy systems, they need to have this pathway nature rather than just a snapshot nature.
How far were you modelling?
We were not modeling so much in time, but in terms of carbon constraint. So in this case, yeah, up to 50 to 70%, I think, is where we were going. Now, time, it's better to model with time, because if you model with time, you can look at your assets, so you can look at your existing assets and your investments, and you can model the retirements and new investments. So you can also allow for the fact that there is some natural turnover, which gives you potentially some opportunities to improve the performance of the technology. So I have a whole other lecture, which is called, it's interesting enough, it's called Gas in a Low Carbon World, because I think that's one of the really interesting questions for the future is, how would we use gas intelligently in a low carbon world?
And I'll make the next question the last question. It's from this side of the room.
Peter Burgess, formerly of this parish. I was just wondering how much there's a question of, in the developed world, we've already built our cities, whereas in the developing world, is how, roughly speaking, the question is, how much effort should we put into fixing our problematic existing cities versus trying to get things right first time where they're being built from scratch?
I wouldn't say it's either or, because most of today's cities will also be the cities in the next 30 years. But definitely the new builds are well worth getting right. So some very interesting discussions going on in Mumbai and Cairo, where they're thinking about two options. One is to spend quite a lot of money to improve the sustainability of the cities, and to do that to allow for growth. But there's an argument in the urban planning groups there, and the city council and whatever, saying if we take that money and we build literally next door a new version of itself, but a much better one, that might actually be a better way to do it. So I think the answer is not really either or. It's whenever there's a new city being designed, it absolutely should be designed on low energy, low carbon principles, because that will really save a lot of future headache. But most of the cities that are here today will be the cities that people will be in. If I go back to my my second slide, that will just show you. So this is a 60-year picture. And you can see, although there's some transition in there, you can see towards the right-hand side, it's stabilizing a lot. So a lot of those cities are going to be here. Yes, there'll be new cities, and a lot of the new additional 2 to 2.5 billion people will also be in new cities. So those definitely, but a lot of those will be in existing cities. And the problem is that the asset base of the building side, it's 30 to 60-year turnover. So it's very slow. So we need all kinds of clever things to do with all of those buildings.
Okay. Well, Nilay, I'd like to thank you very much indeed for giving us such a clear exposition of a fascinating topic, and indeed being so free with your time in answering questions and spending almost as long time interacting and answering questions as you did in your initial lecture. Thank you very much for that. I would just say I thought you were fantastically modest in saying that just being a process systems engineer, it was almost natural to say after having reduced energy consumption in process plant, the next question was cities. I thought it actually took terrific insight to ask that question and ambition to attempt to answer it. I think there's a lot of people who would have asked that question and then straight away put it in the too difficult bucket and forgotten all about it. And then to show the leadership to bring a team of people together capable of doing systems analysis across so many complex and interacting systems, and then to draw out of it insights, policy implications, and to talk to such a wide range of stakeholders along the way. I think it was a terrific exposition. Thank you very much for sharing that with us.
Yeah. Thank you.